Okay, so now we will continue with the parallel coding today. So far we've done OpenMP and parallel1.c, and we've added OpenMP plus AVX in parallel2.c. So we did this for the direct summation kernel, which, the n² kernel. So now we can start adding these capabilities to step 1, 2, 3, but I want to keep these step codes simple, so I'm not going to modify these codes directly. So maybe we can continue to do parallel 3, which is like a parallel version of step 1, and then, like simply keep incrementing the parallel numbering to make each of these steps. So let's first copy over, because step 1 we want to turn into parallel 3.c. So I'm going to copy over parallel 1. So I'm going to basically do like an OpenMP version of step 1. Okay, so maybe even better. So because I want to keep the naming consistent, maybe I can name it, instead of step 1.c, I can do like a step 1, parallel.c, so that you know what, this code is. Okay, so if I want to do OpenMP parallel here, first of all, so what we did this morning was just this part. So the checking the answer can be done very fast now. But so let's see what happens when we do pragma OMP here, because it might do something strange, because we have a printf here. So what happens if you printf from OpenMP parallelized loop? You'll have two threads printing at the same time, and you'll see the order of the print will be strange. So just so you get familiar with what, sort of what the OpenMP is doing, as an experiment, it would be interesting to do pragma OMP parallel 4 here. And we need that private J thing here. Another experiment I can do is to remove private J and see what happens to the answer here. That's one other experiment that I can do. But first I'll do this one. So I've added OpenMP parallel 4 to the same loop that we've been doing this morning, except this one is checking the answer, so it has a printf at the end. Okay, so let's compile this with the same commands that we've been using, OpenMP and then AVX. No, I'm not using AVX now. Okay, so then well, I guess it's hard to tell what order this is printing. So maybe I'll print the counter, I. Okay, so it seems to be printing in order because it's not executing in parallel at the moment. Because I've set the default number of threads to 1, by default it doesn't run in parallel. So if I set to 2, what happens? It's still printing in order. So let's look at the timing. Well, maybe the timing will be too short because we're only calculating for 10 points in step 1. So maybe if I increase the number of points that we calculate from 10 to, let's say, 1,000, then maybe we will see something in the timing. But then it will print 1,000 things, so it will print a lot of data. Okay, let's see what happens. See, now you see a little bit out of order stuff. So now, when it was 10, it didn't make too much of a difference. I think, either one started a little bit early, but it's just 5 things to process per thread, so it was very fast, and it was in order. But now, you see that it's the printf inside that double loop. So one of the loop goes from obviously 0 to 499, and then the other thread handles from 500 to 999, and it's both threads are printing, but not synchronized. So you see the I being printed from, so this is thread 0 printing, and this is thread 1 printing. You see that they're handling different parts of the loop that goes from 0 to 1000. So printing from OpenMP, loop is an interesting experiment if you do it like this. Okay, so now let's see what happens when you remove private J. And because we're printing the answer, you'll see something happen. Well, if it doesn't segfault, okay, so now you don't see too much of a difference, but that's because I'm doing this calculation. So this is not a very good case to check if the answer is correct, because they're, the numbers are very different. So let me change this back and use a different code to do this same experiment. Private J. So the code that was giving a good comparison was this one. So this code was actually, if you print the answers here, if you do like a printf in parallel 2 code, this one is giving very, very similar results to the previous code. So you should be getting exactly the same, almost exactly the same number if you do this correctly. So let me print these 2 things here. I don't want to print too many things to the screen, so then let me compile for parallel 2 now. This is what happens if you compile AVX code without MEAVX. Okay, and okay, so now it's giving you these answers here. And when I remove the private, what will happen? So some of the the numbers we're matching are still matching, as you can see. Yeah, so not having the private thing is not affecting too much for now. Maybe I have to increase this number here to see the real difference. It's still matching quite well. Okay. Yeah, so it seems that not having this J private is not harming the result too much, but you still need to have this here if you want a proper OpenMP program. So I'll just return this code to the original state. Okay. All right, so that was the experiment with parallel 2. Now let's go back to step 1, P. Okay, so this is the OpenMP parallel version. So see that now this time it didn't put the 400 numbers in between. So it's not reproducible. It depends on when you execute. If you're lucky, sometimes. No, sorry. This is because I didn't put the OMP num threads here. So I'm just running on 1 thread by default. If I put here OMP num threads 2, then it executes on 2. But you see that the ordering here is like completely random. Sometimes 499 is at the end. Sometimes 900 is at the end. So this has an impact on your debugging, because when something goes wrong and the answer is different every time, then you have a hard time determining what's wrong because it's not reproducible very exactly. So once you start doing parallel programming, the debugging becomes a little bit difficult because of these issues, because the answer changes, the order which the answer appears changes a little bit, even if you do printf and try to check something. So this reproducibility, you need to be somewhat aware when you're, it's one of the key things to worry about when you're doing debugging of parallel code. Okay, now, so far we've only parallelized this last loop. This we have already been doing since this morning. And now we are doing printf and just printing inside this OpenMP loop. But what we could also do is we can also use pragma OMP, for example, for this loop here and this loop here. Okay, and so another thing is if we try to do it here, something a little bit strange is going to happen because of this function here. So this random number generator will not generate the same random number if you use OpenMP. That's because these functions, how they function is, first there's something called a random number seed, which is like a number which the generator starts from. It's like an initial condition of the random number generator. And that number sort of starts from the seed, and then it gets incremented, and then the algorithm that it uses inside is reproducible as long as it's running on the same thread, because it follows the same sequence. So when you parallelize it with OpenMP, you'll end up having for each thread the same random numbers. So well, we can try to experiment and see if this is the case. So because when we're discussing all these issues about OpenMP programming, I want you to run into these problems that you'll face at some point now, so that you understand what you need to worry about when you're using OpenMP. It's not just about putting this pragma and parallelizing the loops. That's not enough if you want to do OpenMP. You need to know like these issues. What happens when you code in OpenMP? What happens to these things like random number generators? Okay, so just for the sake of readability, I'm going to reduce this number back to 10, or maybe 20. It can fit on the screen. And then I'm going to use pragma OMP parallel 4. I don't need the private j thing here because I'm not using j in this loop. Okay, so I'm going to print the index I and then xi and yi generated from the random number generator in OpenMP in parallel. So let's see what happens when I first run this thing on one thread. So okay, so it ran. Why is it printing twice? This other thing is the printing at the end. So let me suppress that because I don't want to contaminate the screen with this other print. Okay, so when I run with one thread, it generates these following random numbers. X is sort of incremented by 2, so not incremented, it's offset by 2 in the x direction. So the numbers are between 2 and 3. Okay, this generates, on the y side, it's numbers between 0 and 1. So you see these numbers. Okay, and then when I run this with OMP num threads 2, the following will happen. Okay, so maybe it's difficult to compare the numbers side by side. Yeah, you'll have to remember. No, let's do the following. So I can run yeah, let's run. Let's run from inside this split window so that you can see both sides. Okay, so on this side, I will run with OMP num threads 1. Why is it showing the same thing? Okay, for some reason it's not doing what I want it to do. I'll do it this way then. Okay, so I'll just use 2 screens. Okay, so now you can see the two parts on the 2 different screens. So this one is with OpenMP threads 1, and this one I used OpenMP 2, like 2 threads. So the numbers are not the same apparently. So for example, 1 was 2.536 for one thread, but now it's 5.2. It's sort of the second number, it looks like. Yep.
So for 11 it is
11.
the random part is from the y part is same.
Oh yeah, so well they're both the same from here on. 5, 1, 5. Yeah. So for this one, the order at which it was executed probably changed. So I should be able to find this 3.6 somewhere. No, it's like it skipped 5.2, 9.3, 7.6, 8.7, 8.1, 2.7, 8.6, 2.1, 2.5. And then it skips the 2.0.0. And also the y random number for 0 is different, it seems. So 00985 appeared here. So it's like, so it's because I'm generating random numbers for x and y, and the random number generator for y is being executed here in this case. So this is thread 2 executing the drand before the y random number generator for this was executed. So this one took the value here and put it here into the x of the first one. And then when it tried to generate this one was already taken by 3.6 somewhere. So it should be appearing somewhere, 3.6. Yeah, it disappeared. And now, okay. I think there's another random number. Is there a random? I have to look at my code to check what. Yeah, it's generating other random numbers. So this is the reason why it disappeared. So if I only had one drand in this entire loop, then you will see the correspondence between everything. But so the thing is, every time drand gets called by someone, it generates a new number. And I think if the other thread executes the drand before you do for a specific entry, then it takes that random number before you can use it. And so that's why, So in conclusion, if you do OpenMP parallel for your random number generator, you won't get the same random numbers. So you need to be careful not to parallelize where you're generating random numbers if you want the results to be reproducible. Okay, or maybe there's a special way to even code in OpenMP, still do parallel, but generate the same pair of random numbers. Maybe you can put here like a random seed that is very different for everyone, and then they'll generate different random numbers. Okay, but I think in general this is a consequence of doing OpenMP. One of them is that you need to be careful with these random numbers. Okay, but let's not worry about that for now and just parallelize everything and see how much faster it gets. So just do pragma MP parallel 4 here, for here, and so all the loops I'm parallelizing with OMP parallel 4. And I'm going to check, so if I run for a big enough problem, then it's going to show up in the timings, the difference between these two codes. So if I do like a time, it's taking 1 second. Okay, and then now if I do OMP num threads 2, you see now it's not the same as before. So before, in the first, like parallel 1 and parallel 2, this was becoming 0.5. Now it's not very parallel. So let's see what happened. It doesn't look like the code is getting very fast. So everything is done in OMP parallel 4. So this part is done with parallel 4. Also, if we go down P to M, this loop is also done with parallel 4. And this loop is done with OMP parallel 4, and also this one. So everything is quite parallel, it seems. But for some reason, it's not speeding up very much. We don't know what's causing this. So now, let's use the getTime function to time each part to check. We want to check which part is slowing us down, or I mean, not which part is not very parallel. So let's use this function again here and define it inside the step1.c so that we can check which part. So let's time all these loops. Let's do like get time, okay, and here we do like a talk and then a printf. So this is a nice way to find out what is taking how much time. Okay, so let's time this part separately. And M2l we can just leave alone because it's not really parallelized. And then this last part. Okay, so now it will print all the times of the different all the different timers. Okay, so it turns out the other parts are not taking any time at all. So something strange is happening to the final loop, it seems, because that's the part that's taking all the time anyway. Yeah, so I wonder what's happening, because now we have the same loop that we've been parallelizing this morning, and it was like 0.56. But now it seems to be close to 0.8. And I'm using the same thing here. I don't see any difference. So I wonder what happened. So it's this loop here. We've been using the same thing this morning. I don't think it's any different. And now it's not speeding up for some reason, and I am not sure why. What could be causing this slowdown? Yeah, I don't really understand what's causing this slowdown, but as you can see, it's not printing, so it's not the printing that is slowing it down. It's just when I execute with one thread, it's taking 1 second, and okay, now this is very strange, because now it's slowing down. Okay, this is very strange. What does anyone know what's happening? I'm just parallelizing the same thing we did this morning, and this part is taking. I have a tick. Oh wait, maybe do I have a talk up here? Talk. Yeah, so I'm doing talk get time here, and then at the bottom I have tick. So I'm doing talk here, and then a tick here, and I'm subtracting the two. So so it should be okay. I think it's. I mean.
Is there a data dependency of R for minus?
This one. Maybe this is the problem. Yeah, you're right. Okay, let's try this and see if this fixes it. Yeah, you're right. So there was a difference between the code in the morning. This is another good example. I'm glad this happened because, okay, so just to review what happened now. So before in the morning, this was double R because R was not defined before. But in this code, I use R for something else before, and then I'm not redefining. I'm not defining a new R here. So it wasn't private. So now you see the effect of having something private. If it's not private, it's shared, and then when a variable is shared, it creates some, like a conflict between the reading and writing or no, actually this is just writing, but since it's shared, many people are trying to write to R at the same time. So the same memory address gets accessed many times, and then it sort of creates pipeline stalls in the execution. So basically having this private assures you a safe execution, and therefore it will scale. So basically private is good. Private means it's parallel. If it's not private, if it's shared, then it's not very parallel. So here's a good example of why you need to make things private. The similar thing should be happening with J, but I don't know why it worked for J. But yeah, this is a good reason to make variables private. So if something is defined outside, if it's defined inside with like double UID, double DX, double DY, these are already private by default because they're defined inside the OMP loop. But this one is not defined, so you have to make it private. Okay, so this was a good example of, correctly adding private to your. So now we have step 1p now has all these timing results. But again, so this also is a good example of how fast the FMM can be because, well, it's not a proper FMM, but it's a comparison against the direct computation of everything against everything versus using the FAR approximation. So P to M takes this much, or no, I think this is initial condition generation. So P to M is this 0.000053. P to M takes this much time, and L to P takes, the combination of M2l and L to P is this thing here, and it's taking only this much time. So the sum is the amount of time it takes to generate roughly the same answer as what you get from the final loop of summing over, all 0 to n-1 and 0 to n-1 in that double loop. So this is the algorithmic speedup. This has nothing to do with the speedup coming from parallel execution. It's not AVX, it's not OpenMP. This is the speedup coming from the FMM. Because you're using a different algorithm to calculate P to M, M to L, and L to P, the time it's taking to calculate that is only this much. So you see how important FMM can be from just these numbers, the timings. So today I'm showing you the timings of everything. So now you see the significance maybe of how fast these methods can be. And then it's completely different. You'll have to wait many years what would take for, like a few hours for this one if you had the same algorithm. So now maybe let's move to step 2 because I'm not going to spend too much time on each of them. I'll just move to step 2p and just do what I did for step 1p. I'm going to take all these things like the get time function because this is useful. I'm just going to copy over this thing to step 2p. Okay, and also, these tick-tock functions I'm going to like this one would be a good one to copy. Okay, and I'm going to time the P2M, M2l, and all those M2l, L2p, and then I'm going to add all the pragmas for the OpenMP. Okay, so now I'm just going to compile with the same command that I've been using for step 1p to compile step 2p and then execute it on 2 threads. Okay, so now because n is very small, it's not showing any difference. Let's make this large. Okay, I need to stop printing the answer here because it's contaminating the screen. Okay, so let's see, what's this part? Ah, the P2P, okay. So now this is the P2M, M2l, and L2P part. But this P2P part that is doing, if you remember the slides from, I think, the second day, yeah, like it's doing, oh no, maybe this one. From the first day, it's doing this calculation here. So step 2, it's doing the near and far separation. So like in this figure, and let me show the timings along with this picture so that you can see what's taking how much time. So this thing here that's taking 0.012 seconds in the timings is the near field calculation. So as long as the problem that you're solving is like almost the same size as the original box, and you have to do that 16 times, you know, you're not really saving very much. So this is the part, near, that's taking this much time. This 0.010395 is the calculation of the whole thing. So of course, if you have to do this calculation for 3 by 3 boxes 16 times, that's not so different from having to do 16 by 16, this 4 by 4 calculation. But the other parts, for the far, this part remains very small, you can see here. So when we apply this to step 3, which is, actually I should be showing the other slide that reviews the steps. So step 3, Morton index, and then, yeah, maybe if I go to step 4, then doing this whole thing directly should be much larger than the near field that I'm showing. So this part here that's doing 0.012 is now much smaller if I apply it to step 4. So then I should see the true, start to see the true significance of FMM. So I'll try to cover, I'm sort of running out of time, but maybe I'll at least do step 4 to show you how much speed up you get from FMM. So let's do step 4P. So step 4 in parallel, and I'll just embed the same timers. Okay, so first in front of P2M, and then here, and then after M2l, okay, and after P2P, and then after check answer, I will add the same here. Okay, so now And I need to not print this thing here. And maybe increase the number of points slightly. So even with this, okay. Thank you. So even with this scale, we still don't see too much of an advantage of doing. And now that we're doing so many boxes, if we go down to like level 5, this part is starting to become expensive. So still, we need to have the full FMM to actually see some advantage between this part and the other part. So let's see if that's. So if we go all the way to maybe step, which one is the full? Yeah, step 5. Let's try step 5 and see what happens. Okay, so I'm going to copy everything again to and copy the timers and start from P to M. And this time I have M to M and these other things too. So but we just need to make sure that the P2P part is not taking the same amount of time as the direct for the whole calculation. Okay, so now let's see if the I'm still printing this thing. I can't see the output of the timings if I have this. Yeah, okay, so I need to increase the N to see the effect. Yeah, still, even with this, I don't see too much benefit of using Okay, so still, even with this code, maybe I should still show the timings. If I run, so I ran a fairly big problem with a deep level, so it's doing this multi-level thing. And this part here, as you can see, is the M2l kernel. So it's like these parts here, between the red and blue box. And this part here is the P2P, the direct part. So it shows you that these parts are the major contributions from the FMM timings. So that you know now from experience. But still, this is the direct for everything against everything, and it's still not so different from the timings of these. So there's something inefficient in the way I'm writing this code, and I know that it's inefficient. I just did it to show you the simplest FMM. So this very simplistic FMM doesn't have the performance that we want. Mainly because, see here, what we're doing is we're actually looping over everything against everything. So we haven't really got rid of the double loop of n squared. We're just artificially identifying the neighbors like this. But since the calculation we do inside this kernel is not so much more compared to the calculation we're already doing outside here. We're doing multiplication and putting this inside IX. And then here we're doing absolute value and subtraction. All these things are done for n square number of loops. And so the other loop that does just this thing for this n square calculation is taking almost the same time. So this comes from the inefficiency of how we are programming the P2P. This is the reason why I did steps 6, 7, and 8, is to make this part and the other parts efficient. So because I ran out of time, I'm going to leave it as like a homework to do the same thing to step 6, 7, and 8. You can find the timings get better and better for the more advanced. And that's why I had to do incrementally more. So it's not that I was making FMM intentionally more complicated. These are actually necessary steps, 6, 7, and 8, to actually make it faster. So you'll see this when you do the timings, because this is the simplest multi-level FMM that you can program. So conceptually, you can understand what the FMM is and how to program and how it's functioning with this code, but you won't have the same speed. So I'll just let you see that this is not sufficient if you want a fast working FMM code. Okay, so I think we covered a lot of the parallel programming issues today, some by accident, and now we know how to time, how to make it parallel, how to compile OpenMP and AVX code. So you've learned a lot of these basic parallel programming tools, and also the difference between algorithmic speedup and like parallel program speedup, and that they are both large. So let's try to. So tomorrow I'm going to talk about something completely different. But if you want to know more about parallel programming or even like MPI and GPU programming, I have those codes as well, so I can give you something if you want. Okay, so today we'll finish with this for today. Thank you very much.